All right, good morning and welcome to Monday, October the 5th, AP Chemistry. Today we're going to be doing a lab. It's called Beer's Law Lab. Okay, and as you can see in the handout in front of you, it involves spectroscopy. What do you think spectroscopy measures? What does spectro sound like? Spectrum, which is light. Scopy means look at or measurement of, okay? So we're going to be looking at light, okay? And it's going to be a comparison between light in and light out, okay? And so you have E2 is the energy of the photon going in, and E1 is the energy that is coming out. Some's getting absorbed by the solution, okay? If you turn the page to page 3, it kind of shows what we're going to be doing right here as far as shining a light through a solution, and we're going to be measuring the in and the out, okay? We're going to be measuring the percent absorbance. Okay, how much light is getting absorbed? Now, what do you think? If the solution is lighter or darker, is it going to absorb more light as the light's passing through? Darker, right? Okay, because obviously the darker it is, the less light that's going through on the other side. So we can use this to measure the concentration of the solution. But first, we have to have a curve, a standardization, a calibration curve. And so we're going to have to make a curve, which looks like on the back page here. We're going to have to make a curve of known concentrations. So I know, okay, at 0.1 how much light it's going to absorb, and at 0.08, 0.06, 0.04, all the way down, and then we're going to be able to know exactly. Then if I give you any concentration, an unknown concentration, then you'll be able to find what the concentration is from your graph, okay? Now, Beer's Law, I always say this is a college prep class, so it's only logical that we learn Beer's Law, okay? But it has absolutely nothing to do with beer. I think it's the guy's name. But it says that the absorbance is equal to epsilon, which is an absorptivity constant, times the path length. How far does the light have to travel through? The farther it goes, the more light that's going to get absorbed, times C, the concentration. A lot of times they just say absorbance is equal to A, B, C, okay? Now, for us, we're keeping, let me just say, is equal to a constant, okay? B is the path length. C is the concentration in molarity. A is the absorbance. That's what we're going to measure. Okay? Now we're going to be using these things that are called a cuvette. Kind of like a Corvette, but the cuvette is basically a test tube. Okay? But it's a fancy test tube. It's an expensive test tube. Most test tubes, 12 of these would cost $1 at the most or so. This box costs $50. Okay? So we keep these separate. It's got a little arrow on it, okay? But because they're expensive, they're all pretty pretty much the same, but we still want to kind of use the same one, but the path length, for all practical purposes, is going to be exactly the same, within, you know, millimeters or less, you know, difference between one cuvette to the next, okay? So our path length is constant. This is a constant. So in a sense, this is y equals mx, right? You have two constants that would combine together to make your slope. So it's telling me that the absorbance and the concentration, what type of proportion? Direct proportion, based on math, okay? Just again, I stress, you learn y equals mx, general formula in math, to apply it to a real subject in real situations, like Beer's law, absorbance is equal to a constant times the concentration. It tells me these two things are directly proportional, and this will be the slope of my line. In this case, the slope's not going to really tell us that much because it's a combination of two things, okay? But the thing is that if we make our solutions accurately, we should be able to get a straight line when we plot all of our points. All right, now, if we go to the actual procedure page, the one that's by itself, okay? It says to make the solution, it says to make, how many grams to make a 0.25 molar solution of copper sulfate. You see that right there on A1? You're going to change that to a 0.100 molar. Procedure A, directions 1, 0.100. The 0.25 is too concentrated for the machine to pick up. I copied this lab from somebody else, and their machine was better. Okay? Now we're going to use a volumetric flask. Okay, and they're out of there. What do you think a volumetric flask measures? Volume. But it's going to be only one volume. It's a volumetric, it's a measured volume. And since it's a 100 milliliter volumetric flask, what do you think the measured volume is going to be? 100 milliliters. So it's going to look, and I'll show you in there. I meant to bring one. Well, I might put one. Then again. Oh, yeah. Okay. So here is your 100 milliliter volumetric flask. First off, it says 100 milliliters right there. But there's no other markings on here except one line right here. Okay? That's the 100 milliliter mark. This is designed very, very accurately. This is one of the, if you're making a solution, the AP has to make a solution, you want to use the volumetric flask. Okay? So we're going to measure our solution down in here, our solid down into here. Fill it about 2/3 full with distilled water. You don't want to fill it all the way full because you want to have room to shake it. Okay? And we have lids that you can put on top of it as well. Okay, so you shake it up and get it all dissolved at 2/3. Then you add the water to where the bottom of the meniscus is just on the top of the line. Okay, and you add slowly, because if you go past, there's no going back. You start all over again. Okay, so we can just add little by little, drop by drop, once we're getting close with this little, the wash bottle. Okay, then once you have that, put the cap on it, turn it upside down a couple of times just to get the rest of that all mixed thoroughly. So now we know we're going to measure the exact grams, so we know moles, we know the exact volume, so we know liters, so we know the exact concentration of our solution. So our 0.1 molar solution is going to be what we call our stock solution. Then we're going to dilute it, and who remembers the equation for dilution? I only gave it to you one time, and I forgot. I meant to stress it more in terms of how you do a dilution problem, but it's a simple equation. Nobody?
Is it mass of a concentrated times volume of a concentrated times mass of a diluted and volume?
You are 99% true because you're remembering an M, but the M is not for mass. So it's the molarity of the concentrated times the volume of the concentrated is equal to the molarity of the dilute times the volume of the dilute. Okay? I touched on that and did one practice problem, but this is where it's gonna come into play. Because you're gonna need now, and this is gonna be a second change, okay, to the directions, is that we're starting with our solution A is now gonna be 0.1 molar. Of both, we're gonna do two things. We're gonna do blue copper sulfate and pink cobalt sulfate, okay? So we're gonna do this, everything we're gonna do twice, make two sets of solutions, and then measure. The actual measuring in the spectrophotometer goes super fast. Making these solutions, I'm hoping we're gonna get done today. If not, we'll just continue in on Thursday. Okay? So, solution A is 0.1, so now I want solution B to be 0.080. So I need to dilute this one, and I only need 10 milliliters of it. Okay? You only need 10 milliliters of it. And then solution C, I only need 10 milliliters of it, but it's going to be 0.060 molar. Solution D, again 10 milliliters, and I'm going to want 0.040 molar. And then lastly, 0.020 molar. And again, you get making 10 milliliters of each one. So this is going to be what we call the stock solution. This is what you're going to work from. So we need to do the calculation. So is this one going to be your concentrated or dilute? The 0.1. That's your concentrated, right? Because these are all more dilute. So the molarity of the concentrated is always going to be 0.1. The molarity of the dilute for B is going to be 0.08. The volume of the dilute is going to be how much? 10 milliliters. And you can leave it in milliliters because it's going to be milliliters, it'll cancel out since it's a ratio. Okay? So we don't have to change the liters or anything. So we have to figure out then how much of this do I need to use to dilute to get to this. Okay? This is the total volume of the dilute, not how much you add. This is the volume you're going to. This is your 10 milliliters. So obviously you're not going to add 10 milliliters of water to dilute it. Okay? So you're going to have to do calculation. Number one, you got to figure out how many grams am I going to need to make this. You're going to make 100 milliliters of this. Okay? So you need to figure out how many grams of copper sulfate, and it's listed in there, how many grams of copper sulfate and how many grams of cobalt sulfate are you going to need to add to your 100 milliliter volumetric flask. And you can weigh that directly into it. You can put it on the balance, tare it, and then just add your solid to it. If you don't get exactly what you calculate, that's fine. Just know exactly how much you have and calculate your concentration from that. If it comes out to, your concentration comes out to 0.099, that's fine. It comes out to 1.01, 1.02, 0.102, that's fine. Just know exactly what you have. Okay? Just try to be as accurate as possible on these. Once we have these, then we're just going to put them into our cuvette, and you just drop them into the spectrophotometer, and it reads it automatically, so that part goes super fast. And I'll show you how to use that machine once we get there and are ready to do that. Okay? Now, we have 4 spectrophotometers. We have 5 people. Okay? I'm going to let you two be a group. Okay, just work across the table from one another, but working and making solutions. Everybody else is going to work on their own. And you'll have your own spectrophotometer, you have your own setup, and I'll kind of show you once we get in there on how to do that. Now y'all, we're going to need to work diligently, work quickly to get done with this because everyone takes forever to make these solutions. Okay? Alright, let's set them up, move them out.